Yeah, everyone, this is Mihir Singhal, and we'll be talking about follow-up on attacks on discussions.
Yeah, thanks for the introduction. Okay, so I guess I'll start with background, and some of the slides might look familiar because it serves a common ancestor. So I'll just try to go through the background real quickly just to refresh everyone. Okay, so cardinality queries, right? That's our setting. This might look familiar. Right, okay, so we're trying to basically sketch either like the size of a set, or like we'll also consider sort of vector case where you have like these sort of sparse vectors and you're trying to estimate their L0 norm. Okay. Right, and our goal here is to like basically have like these maps that take this data set D, which is again either a vector or a set, and map it to this much smaller sketch S of D. And we want it to be small. Sketch should be low in memory. It should be accurate, so we should be able to estimate the cardinality while using the sketch. And also we will look in part at composable sketches. So again, Sarah's already defined this, but just to give a quick recap, if you have a bunch of data, if you have two data sets like A and B, basically the composability property says that your fixed sketch map that maps A to some sketch and maps B to some sketch, it should be possible to combine these two sketches to get you like a new set. And the reason we care about this property, first of all, the problem is sort of trivial without it, right? Your sketch otherwise could just be like the size of your set. You need something. But we care about composability in particular because this is sort of an important property to have in practice, right? If you have a lot of data, one, it allows you to do this sort of distributed computation trick. If you have a bunch of different, if you have a data set, you can sort of split it up into many servers and they can compute their own sketches, and then you can take their union yourself. Or, you might like have a long period of time over which you're collecting data, and you can sort of take sketches for like snapshots of time. And then you can sort of compute like sort of a cardinality sketch over a period of time by taking a union of a bunch of these. Okay, and then really quickly, I'll go through existing proposal sketches. So again, we've seen some of these, but basically it's possible in the non-adaptive setting to make a sketch, whose size is log n plus k, where k is a parameter that depends on the failure probability and the approximation parameter you want. Essentially, k is going to have to equal log 1 over delta over epsilon squared, where delta is the failure probability and epsilon is the approximation parameter. Right, so this has right, yeah. Okay, so maybe before I talk about adaptivity, let me talk about the model of interaction that we're going to use. Right, so basically, for the non-adaptive settings, the model doesn't matter so much. But here, let's say, okay, so basically we have these sets like U sub I, and the adversary is sort of picking the sets to give like as queries to the estimator one by one. And the estimator doesn't get access to the sets themselves, right? The estimator only gets access to the sketch of the set. So there's this system in between that takes the set and computes the sketch of the set. And the estimator has to like look at that set and like return estimated cardinality. So the estimator gets a sketch, computes an estimated cardinality. And then the adversary sees the estimated value and can kind of repeat and like use this information to continue like doing, to continue generating the next set use of ui plus 1 until it can force the estimator to sort of make an error. All right, so we say that the size of the attack is the number of queries that the adversary needs to basically compromise the estimator, to force the estimator to make an error. So if you look at it from the estimator's point of view, right, the number of queries that the estimator can answer is the size of the smallest attack. Okay, so in the non-adaptive setting, right, as I said, we can get k equals log 1 over delta over epsilon squared. So if you just do a union bound, this tells you that the number of queries you can answer, taking epsilon as a constant, is essentially exponential in k. However, this union bound requires this non-adaptive adaptivity of the query, right? This property won't continue to hold for future queries if the adversary is adaptive. So there's this natural question of what happens in the adaptive setting. So here now we allow the input to depend on the previous inputs and the answers that the estimator gave on the previous inputs. Okay, so that was a real quick background. If anyone has any questions about like sort of the setup of the problem now. Okay, great. Previous again? That's it. Okay, so let me talk about what the previous results have been so far. So one of the positive results on these sorts of sketches is the sort of wrapper around a non-adaptive sketch. So if you have a sketch, an algorithm A that has these non-adaptive guarantees, you can sort of put these like differential privacy related or subsampling related wrappers around the algorithm A and get an adaptively robust algorithm out of this non-adaptive algorithm. So it's known here, okay, you can do a sort of simple thing to take like k copies of a non-adaptive algorithm and get an algorithm that can answer k adaptive queries. You can actually do a little better than this using some more advanced ideas and get actually k squared adaptive queries. So again, like if the sketch has size k, we can answer k squared adaptive queries using sort of k copies of the sketch. Yeah. Sorry. If you have A does not have size k, this total sketch has size k because it has k copies of the algorithm A and it's answering sort of k squared adaptive queries. Right, so these are the papers that kind of get these results. I won't go into detail exactly how they do it, but they use sort of a variety of different methods to sort of achieve these wrappers. Okay, so that's the positive results. Now we'll get to some negative results. If the algorithm is like a statistical query-based algorithm, if it looks at some subset of the universe and sort of looks for each, and the sketch is just sort of which elements of the subset did I include, there's an attack that can attack any estimator that gets this sort of sketch, which is based on fingerprinting codes. And so that restricts these statistical query algorithms to the k-squared queries. There's also, this was the talk that was just given. There's an attack on several of the standard cardinality estimators, like the min hash based estimators and other such estimators. And finally, in the universe of linear sketches, there's also recent work that gets a variety of polynomial upper bounds on different linear sketches over various domains, such as the reals, the integers, and finite fields. So I guess we're interested in seeing if these can be tightened and or unified. We want to be able to find an attack that sort of works on many different sketches, and also that can get closer to the upper bound, which is to the lower bound, which is k squared. And in particular, we're interested, as I mentioned, in these composable sketches that I talked about. If you can take two sketches and then take their union. So we're interested in trying to find a general attack for composables. Okay, so now time for our results. So we present this unified attack, which applies for like a variety of classes of different algorithms under some condition, which I'll describe. So in particular, for any composable map under the definition that I gave, we show an attack that causes the estimator to fail in case of forced queries. And under some additional condition on the composable map, we can get a k-squared query attack. And then for linear sketches, over finite fields, and for like this linear sketches and sort of Boolean algebra, we can show a k-squared query attack. And under some additional assumptions, we can show attacks on certain limited estimators over the reals and over integer value linear sketches. Okay, so now I'll talk about how we get this attack. So let me start by talking about let's start by talking about statistical queries as cardinality sketches. Right, so this is like sort of a simple basis upon which you might build a cardinality sketch. So imagine that your sketching map is very simple. Imagine that you take a random sample of the whole universe of size k, and your sketch is just which of these elements were in my original set. So the sketch of U is just the intersection of U and this fixed map, this fixed set R. Right, so imagine that I'm in basically, I'm in this big universe, and these blue dots are sort of the whole universe. And the red dots are, sorry, the red dots are the set R, and the circle. Imagine if these 5 elements were in the set U, my sketch is just these 2 red dots, the ones that were in R, the ones that were sampled. So we can estimate the size of a set kind of naively here. It's approximately the size of the intersection, but like if you scaled it up to the size of the whole universe, I think this formula is not exactly right, but you can take the size of the intersection, multiply it by the size of the universe over the size of the query set. So if you're to try to attack like a statistical query-based algorithm, we might try to identify like what the sample R was. And we might try to like, if we can figure out what R is, we can do all kinds of things with the algorithm. We can just, give it the set R as a sample, and it'll think there was the whole set that I gave it as a query. And the query responder, the estimator's goal is to sort of protect this value R. Oh, sorry, this set R. They don't want the adversary to figure out what R is, so they can keep answering queries adaptively back. And in fact, like a lot of popular sketches in real life, these min-hash based sketches, which I'll describe further later, can be seen sort of as pretty similar to the statistical query sketches. So it turns out that those, a lot of their data is contained in the value of the intersection of some set with the whole query set. Okay, so in fact, our basic thesis is that a lot of sketches are actually very similar to statistical query sketches. And this is in the sense that sort of basically many sketches should basically only be able to look at some small subset of the keys and basically tell you what's in that small subset. And this is sort of the property that we use to like so this is the property that we use to like create an attack. So maybe I'll be a little more specific on this. So the property that allows the attack is the property of having what we call a determining pool. So say we have some sketching map S. So a determining pool is a set L such that basically for any set, for any query set that you give to the sketching map, you can figure out what the value of the sketch should be basically just from its intersection with the query pool. So this kind of takes the same role as the sample set R in the statistical query model, right? So again, roughly, the sketch of U intersect L should be approximately the same as the sketch of U. For U, like taken from a particular distribution. So this is sort of an approximate definition. I won't get into the exact definition we use that has some additional technical details. But basically, you can think of the determining pool property as saying that this map behaves roughly like a statistical query on the set L. Right? All of the information of the sketch S is basically contained in the intersection with this much smaller set L. So, you can always find a determining pool because you can take the set L to be the whole universe, and then obviously the distribution of the sketch is determined by the intersection of the whole universe. But in order for this to be useful as to create an attack, you need to be able to have a small determining pool whose size doesn't depend on the size of the whole ground set, but instead just depends on some smaller set. So does this definition make sense to everyone before I move on? I'm just going to give some examples of this definition, and then we'll get into how to actually make the attack. Okay, so let me start with some examples. So let's look at the hyperlog sketch. So just to give anyone who doesn't know how the sketch works a very brief primer, basically we'll take all the keys in the universe and we'll give them like random priorities. And we'll also randomly partition the universe into k buckets. So we've sort of randomly ordered all the elements of the whole universe here. And they're sort of ordered within their buckets. And the hyperlog sketch, very roughly speaking, is essentially just reporting the highest priority key in each bucket. I won't get into exactly like the space saving tricks it uses, but its information is sort of contained in just the identity of what the highest priority key in each bucket is. But the point is, okay, so for an example, if this is our query set S, then its sketch will just be like the top element in each bucket from the set S. But the point is, if you take this query set S to be like this random Bernoulli set that we take for the determining pool, almost every bucket will have like some element in the top like log 1 over delta elements with probability at least delta. So right, so basically if we take this, the top like log k over delta elements of each bucket, with high probability each sketch, with high probability, the sketch of any element, sorry, with high probability, each set that you sketch that's sampled in this Bernoulli way is going to contain one element in each bucket from this, and so you can determine the sketch just from the intersection of these elements. So these elements like form a determining pool of size k times log k over delta. And we get into another example, so that you can also do a bottom k sketch. You can hash all of the keys and just take the top h keys as your sketch. So again, if this is my set S, then sketch is going to be like these top 5 elements. And once again, if I take a set, if I take a random set, its entire, its top k elements are very likely to contain the first like k log whatever delta elements of the sketch. So again, I can take sort of these k times log k over delta elements and call these a determining pool, because if I just look at the intersection of this, I can again figure out the whole sketch. Does that make sense? These examples? Okay, great. So okay, so that's what a determining pool is. So now let me describe why I can sort of use them to attack the sketch. Basically, we're going to construct an attack that can roughly identify the determining pool. It can construct basically this mask M that's going to approximate the determining pool. So basically, and if we can do that, right, we can just send as a query. We can first sample like some random query set, and then we can send as a query the union of that query set with the mask. But as I said, the sketch of the set of the query only depends on its intersection with the determining pool. So the sketch of the query is essentially the same as the sketch of the mask. And then, the algorithm doesn't know anything. The algorithm doesn't know anything. It can't figure out the size at all. So that's like sort of the rough framework of the algorithm. If we do this, then it's not going to be possible to estimate the size of the original set. And the idea for this attack is kind of a generalization of some fingerprinting code-based attacks, which I discussed earlier in the background. Okay, so this was a rough overview. Now let me get a little more into detail on that. So first of all, let me just talk about soft threshold queries for a bit. So, as I presented the algorithm initially, the estimator has to return estimate for the cardinality size. What we require isn't that strong. We instead just say, we'll give the estimator, instead of asking it to estimate the cardinality and report it, we're just going to ask it, is the set greater than 2a in size, or is it less than a in size? So obviously, if the estimator can estimate the cardinality, it can also do this. So basically, we're going to construct our attack just by using these sorts of queries. And now finally, here's the algorithm. So this is a bit of a mouthful, but let me just go through it. Okay, so basically, again, as I said, the goal is to try to construct this mask that approximates the determining pool. So the algorithm, the attacker doesn't know the determining pool and is trying to figure it out. So it's going to start by initializing some scores. And I'll call the array of scores C. And basically, the main loop is going to be as follows. So I'll take some sample. So first of all, I'll sample a sample array, which is going to be some roughly constant value from some fixed distribution, which I won't get into the detail of. And then we're going to select our query set by taking this sort of Bernoulli for each element in the universe. So I'll pick each element of the universe with probability Q, and I'll assemble that into a query set. Then I'll take the union of that query set with the mask that I have so far, and then give it as the soft threshold query to the algorithm. So I get this answer Z. I get either 0 or 1 if it's less than A or greater than 2A. And in between, I could get anything. And then finally, based on the result of the soft threshold query, I'm going to update the scores of everything that I actually queried. So these scores will go up for. So if Z was, if the set was in fact big, the scores will all go up, and if it wasn't big, then no scores will have to go up. And then finally, if C's if the score of any element gets too high, I'm going to put it into the mask. I'm going to say this was in the determining pool. I'm going to put in my mask now. And I'll keep going. And for all, future queries, it's going to be part of the mask. Okay, so that's the attack. Now, why should I sort of expect this to work at all? So the basic idea here is that when I give this query, again, because of the determining pool property, you can essentially say that the only thing, sorry, yeah.
Question, that for each x in U, that is.
Sorry, this should be not a script U. This should be an X in the actual query setting. So that's a type. Any other questions? Yeah, okay. So basically, I can say, because of this determining pool property, I can say that the estimator, instead of seeing the whole set U union M, it only saw the intersection of this set with the determining pool. So, basically the estimator is like sort of observing these Bernoulli random variables for each element in the determining pool. It has to say like whether or not my, at the end it has to say whether or not my sample rate Q was like high or low in this sort of soft threshold manner. So basically, it's going to have to use some information for this. It's going to, if it got all ones, if everything in the determining pool was present, it should have to say that the set was big. If nothing was present, it should have to say the set was small, etc. So like, basically in a rough sense, the answer Z should be positively correlated with the presence of the elements that were in the determining pool. So as I run this algorithm again and again, I should see that the scores of the things in the determining pool should rise over time. Similarly, for the elements that were not in the determining pool, the estimator doesn't know anything about them. It should be like completely uncorrelated with what the estimator reports, because they're sort of independent in this sense. So basically what should happen as I run this algorithm is I should see the scores of the elements in the determining pool rise over time. And then as they do that, slowly they'll just be added to the determining pool. You can show that their total score, the total score of the elements in the determining pool rises by approximately 1 over the size of L each time. So it takes about size of L squared steps for all of them to rise to above like sort of some logarithmic threshold. So basically that's, I'm not gonna say that many more details, but that's how we show that if there is a determining pool, then we can do this attack in size of L squared steps that forces an error rate of approximately 1/4 from the algorithm. Okay, does anyone have any questions on that before I get to some applications of the theorem? Yeah.
Does this robustify if you have like an approximate determining pool?
If you have an approximate determining pool. So the notion of a determining pool is already approximate. I didn't say exactly.
There was some like squiggly line.
Yeah, there's some squiggly line. Yeah, there's a delta on those squiggly lines.
Okay.
So yes, to some extent, depending on how you try to weaken the notion. Any other questions?
So where in here can you use various assumptions about the input? Like reals or integers?
I haven't gotten to that part yet. So far, I've just shown that if there's a determining pool, then something is true. Now, what's left is to show that under assumptions on the type of sketch, that there is in fact a determining pool. So that's the part that depends on assumptions. And so I've shown that the min hash based sketches have determining pools already. So that's this attack already goes through on those. But that's it that we'll get to next. So let's first try to apply this to composable maps. So just as a quick refresher, composable maps should support this composition operation that takes the sketch of A and the sketch of B and then returns the sketch of A union B. Okay, and maybe this was a little. Sorry, this is okay. So for composable maps, we can sort of define these sort of combinatorial notions of a core. And okay, the exact definition is not that important, but basically, we have some notion of like a monotone composable map, which is sort of like a well-behaved composable map. It says basically that if you have two like sketches in this map, and like one of them sort of contains the other, then so yeah, if one sketch like can contain the other sketch, then like sort of the minimal element of that sketch should also be bigger than the minimal element of the other sketch. So I won't harp too much on this, but basically, right, okay, so basically, you know, a lot of these like actual maps that we use in practice, a lot of the actual composable maps that we use in practice are in fact monotone, like they satisfy this like monotonicity property, which is some like niceness property of a composable map. And the thing we're able to show, and I won't go into the proof of this, but we can show actually that composable maps have determining pools of size k squared. And furthermore, the monotone composable maps have determining pools of size roughly k. And that just, again, by the theorem that we showed, directly gives us attacks of size k to the fourth and k squared, respectively, depending on whether we assume this monotonicity property. So for every composable map, we have this k to the fourth attack. Yeah.
What is the one?
Hmm?
What is the rank?
Sorry. So there's a line in this. I haven't defined the rank, but let's say that's the size of the sketch. It's an lower bound on the size of the sketch. It's whatever direction makes the theorem work for sketches of size k.
So for your bound for general, do you think that's for your analysis, or do you think that it actually is k squared model?
We don't think it's actually k squared. We think we weren't able to prove a bound of k, but we think we can probably show that there's a determining pool of size k as well. But we don't know how. We haven't found a counterexample. Okay, so that's all I'll say. Composable maps, we move on to the linear sketches that I talked about. So now we have some big sketching matrix A and some query vector V. So the sketch is the product, the matrix vector product A times V. In other words, it's sort of like this weighted sum of a sort of a combination of columns of A. This is not under like our strict definition of composability, a composable sketch, because sort of our composable notion like talked about unions and also like required there to be a unique sketch for any set. So results from composable sets, first composable sketches don't extend directly here. So we have to try to again show by ourselves that these have a determining pool. And the final thing I'll say is that, you know, when I defined all of these notions before, I didn't say anything about sort of the weights on the vectors. And in fact, like we have the freedom to choose like distributions for the weights of the vectors to give us the property that's like sort of the determining pool property that we want. And so that's like part of the difficulty in like showing that the linear sketches have determining pools. It's that you have this extra like degree of freedom in picking your weights. And so let me talk about finite fields. So we need to, again, like in the attack, we need to decide what the entries of the vector are going to be, right? We sampled some set, like this Bernoulli Q to the U, which tells us, you know, which elements of the vector have to be non-zero. But we still have to decide what values to give them to make there be a determining pool. So we can't just give them ones and zeros, because then my matrix can just be one row and it can have a bunch of ones. And then, you know, now A dot V is just the number of ones in V, 1P, but let's ignore that. And then you can tell me exactly how many elements were in the set V. So we have to do something a little better, but we need to basically specify some values so that there's a determining pool. It turns out in the case of finite fields, we can just pick random elements of the finite field. So if I pick each element of V that is already selected to be non-zero, to be just random from FP, I basically get some random linear combination of columns in A, of some specific columns in A. So I've got like this random element of the span of these columns of A. And I can actually show that the span has a determining pool. So I can show this explicitly by like basically saying that, you know, I'll take all the columns of A and I'll pick a basis of those columns. I'll remove those columns. and I'll repeat the process. I'll take a basis for the remaining columns and so on. And I'm not going to go into the details of the proof because I don't have time. But basically, these indices of the columns that like form these bases, if I pick enough bases, I think I need log k of them, or log k over delta of them. Those indices will give me a determining pool. I can figure out basically from the presence of or absence of those columns whether or not, what the span of the subspace will be. This sorry, this proof can also be phrased in terms of the composability result that we already had. So we can show, if we want, that the span of the non-zero columns forms a monotone composable map, and then we can just apply sort of this composable result that we already showed. So these are sort of two ways of proving the result for finite fields. In the end, we get a k-squared size attack on finite fields. And then I'll note that we can do something similar-ish in the real RAM model. We can prove that there is a determinism pool in the real RAM model which is sort of the model where you have real numbers but with infinite precision, and you sort of don't give bounds on the real numbers in the sketches. So this result extends to the real RAM model for real valued linear sketches. And finally, let me talk about Boolean linear sketches. So this is just like a linear sketch, but on a Boolean algebra where I just take like ors instead of pluses and ands instead of times. It turns out that these are also monotone composable, and I can write a determining pool explicitly, which is basically all the columns. So we have a bunch of rows. Some of the rows are sparse, and some of the rows are dense. A dense row will almost always give you 1 when you give it this random query. So we can sort of ignore all the dense rows. And we'll say that our determining pool is just all the columns that have a 1 in some sparse row. So it's like these columns are the determining pool if these are the two sparse rows in my matrix. And again, I'm not going to go through the details. You can show this the determining pool, and that therefore this gives you another k-squared size attack. And this means that if you take like an integer or real linear sketch that only cares about the sparsity of the output, basically, a lot of these linear sketches in practice, they take some matrix, like hit the vector with it, and then ask, how many non-zero elements were in this matrix product, or which of them were non-zero. Basically, if you have a sketch that looks like that, that's basically just a Boolean sketch up to like linear combinations that might equal 0. So you can show that if you only use a sparsity structure in an integer valued sketch, then there's a k-squared attack just resulting from this Boolean attack. But this still leaves open the possibility that there is an effective sketch with integer values that sort of that uses like more information about the product A times V. Okay, so those are all the results I have to talk about. In conclusion, so we've shown these tight k-squared attacks on various classes of sketches, and k to the fourth are general composable sketches. And yeah, there are several open questions. We kind of want to improve this to k-squared as well. We wonder if you can generalize this type of determining pool-like property to things that are not just cardinality sketches, maybe F2 sketches or something. There's this question about general integer sketches that's open. And finally, the error rate, this is a small one, but the error rate in this attack that the adversary could force was 1/4 roughly. In principle, this should be, as far as we know, you could get an error rate of 1/2. I think the techniques that we use kind of bottom out at 1/4, which is interesting. Yeah, that's all. Thank you. Yeah.
Which part of the linear sketch does not satisfy the requirement composable sketch?
Right. So the definition of composable that we use requires like the sketching map to be a sort of a unique map for a set A. Like it requires it to operate on sets basically. And you take a set A and a set B, and you should be able to find the unique sketch of their union. But so if you have an integer linear sketch, you have like some entries that are 1s and some entries that are 2s.
As
So the second one is the error rate.
The error rate is
It's like the error in the approximation.
It's the rate of, no, the early approximation is epsilon, it's the like frequency of errors. It's the frequency with which the algorithm commits an error. So as I run this, L squared times, we show that, in fact, like on 1/4 of these queries, the algorithm must have made an error. And in principle, this could be 1/2 because it's answering 0 or 1. But yeah, we don't know how to show that, or if it's possible.
Alright, I think we're done.